So we've been talking a lot about our colligative properties and how we go about starting to identify or kind of measure the effect that a certain concentration has on these properties of our different solutions. And so we've talked about freezing point depression, boiling point elevation. Our other piece to talk about is what's called our vapor pressure change. So when we say vapor pressure, we say, what is a vapor pressure? Well, if you got a liquid, a certain amount just naturally does actually vaporize. Now, this doesn't happen, there's not a big pressure change or vapor that's created, but there is a measurable vapor. And so certain things that vaporize more easily or take less energy to boil off have a higher vapor pressure. When we say vapor pressure, it is in a sealed container. When you have a liquid in a sealed container, there is a certain amount of liquid particles that escape as a gas, and it creates a little partial pressure above the surface of the solution. Eventually, we reach equilibrium, and every time you would lose a liquid particle to gas, you'd get a gas particle back as a liquid, and so we get kind of this equilibrium or this kind of status quo, if you will. And so we're going to actually start to figure out what happens to that pressure, that little vapor pressure above our liquid, if we change the concentration of our solution. And what's nice is we kind of see a similar trend in terms of what we're thinking about when we think about our intermolecular forces. The way we can calculate this or measure this change in the pressure is what's called Raoults Law. The vapor pressure of a solvent above a solution decreases when a solute is dissolved into the solvent. And this makes sense. If you are adding stuff to the solution, you're going to increase the intermolecular forces. You're increasing the attraction between the particles. As a result, fewer of those particles are going to be able to escape into the vapor above the solution. And so we see a decrease in the pressure, typically. We do need to make a quick definition here, non-volatile versus volatile. A non-volatile substance or a solute is one that does not vaporize easily, stays kind of as a solid or a liquid. It doesn't want to vaporize. These would be anything that is typically covalently bonded, that doesn't vaporize easily. You could also have electrolytes. These are ionic compounds that also don't vaporize easily, your salts. So sugars, salts, a lot of our organic materials, we're actually going to be doing a lab with urea. That would be also a non-electrolytic covalently bonded solute. These are non-volatile. Things that they're pretty stable at room temperature when we say non-volatile. Our volatile solutes are things that vaporize easily, like alcohols, ethers, your alkanes. Gasoline, octane, is considered a volatile solute. And the reason we got to distinguish these is our non-volatile ones do what Raoults Law says. It's going to lower the vapor pressure, but our volatile ones actually add to the vapor pressure because they also turn into a gas and add extra pressure above the solution. We're going to look at examples of both of these, fear not, but just a real quick distinction when we think about, okay, non-volatile, vapor pressure is going to go down. Volatile, the pressure is going to go up. Cool. So let's take a look at it, kind of an example and kind of the math here. And so the formula here at the top is pretty straightforward. The change in pressure is going to be equal to X solute times P naught of the solvent. Wait a minute. Oh, okay. Remember that X is our mole fraction. We would have to find moles of everything in the solution. We would take the moles of the solute divided by the total moles in the solution. And then we're going to multiply that by what the original pressure of our solvent was. Whatever we would have normally seen for the pressure of that, usually water, but of that solution, multiply it by the fraction. And that's going to tell us how much the pressure is going to change. And then for our non-volatile substances, for example, like our glycerol, which we're going to look at here in just a second, we would actually say that, okay, it's going to decrease by that much. We would go back and subtract then from the original pressure to figure out how much has actually gone about our change. So let's take a look at an example here real quick to make sure we can kind of work these types of calculations and be able to navigate what's going on here. Whoa, that's not the right button. Ooh, come on. Cool. So let's look at an example here. Sorry, I'm trying to get the wrist guard up so I'm not scribbling all over like I just did. Come on. You can do it. You can. Nope. Sorry, I got a. Come on. There we go. All right. Sorry about that. All right. So let's just start by figuring out what we've got. We're trying to find the vapor pressure. when we've got 10 mils of glycerol with a specific density as provided here, we also got the formula of glycerol, is added to 500 milliliters of water, both at 50 degrees. At this temperature, our vapor pressure of the pure water is 92.5 torr, and its density is a little less than 1, which makes sense that our volume has increased due to our increase in temperature. So here is actually our P naught of our solvent, is at 92.5. And so we, I think, need to start by figuring out our moles, but we didn't get grams, we've got milliliters and density. Okay, I'm just gonna organize my work here a little bit. I'm gonna have a glycerol part. We're gonna have a glycerol portion and kind of our water portion. Let's do the glycerol first. So as we're looking, we knew the density was 1.26 grams per milliliter. And we're trying to figure out how many grams of that we put in there. If we put 10.0 mils in, well, to solve for X, we'd multiply those two together as our milliliters are going to cancel here and we get into grams. For our glycerol, that means we ended up with 12.6 grams of glycerol actually being added into the solution. If we go to the molar periodic table, we can find the molar mass of glycerol. For glycerol, our molar mass is 92.09 grams for every 1 mole. Which means we added just a little bit, a little less than a mole here. We got 0.1368 moles of our glycerol that we're adding. Cool, so now we know how many moles of glycerol we added. That's great, we need that for the fraction, that X value. Now we gotta go back and look at our water. Well, I think we're gonna kind of do the same thing. We know the density of our water here was 0.988 grams per milliliter. We're trying to solve for how many grams of water we put in there, and we put in 500 mils. Cool, so we would multiply together and we find that we actually have 499 grams of our water that was added in here. Cool, we can go from grams to moles using molar mass, 18.016 grams per every 1 mole of our water. And now we know that we've got approximately 27.69 moles water. Cool. I think we got everything we need now. So we're going to figure out how much the pressure is going to change. And so we're solving for delta P for all of our physics people. Delta means the change of. So we need, if we're going to find that change, we need the mole fraction of the solute. Well, the solute here was the glycerol, the thing we had less of. That was the 0.1368 moles of that. We're going to then divide by the total moles to get the fraction. Total moles are going to be the moles then of that glycerol plus the moles of our water, which was the 27.69. You'll notice I'm not too concerned about sig figs quite yet because I'm going to go ahead and round right at the end. Cool, so I've got my fraction set up there. I got mole solute over total moles. And then I need to multiply by the original pressure of our solvent, which is that P naught, the P with the little 0 next to it. So our original pressure was 92.5 torr. Now the good news is we've got everything set up here. These would technically also be mole and mole. Moles all cancel out. We got just our unitless fraction times torr. Our final answer would be in torr. So when we actually go ahead and multiply all that together in our calculator, we get kind of a small number. I ended up getting 0.454 torr on my calculator after I kind of ran this. Remember, there's going to be a little wiggle depending on how you estimated and or rounded. The best answer is going to be to leave it all until the end and then just round once at the end. Good news, though, is when we actually go to find the final pressure, we know that the P final, the final pressure, is going to be our original pressure, which was 92.5 torr, minus this change in pressure because we've added more attractions. And so when we look at decimal places here, I think we're going to the 10th place because of our sig fig and decimal rules. And I think regardless of kind of how you rounded this out, it's going to kind of come out to be the same, I believe, 92.0 torr for our final pressure after we've made this solution. So again, the math is pretty straightforward. It's just making sure we're following through and paying attention to what numbers mean what, so that we can get through to kind of our final piece of the puzzle. Cool, next video coming back, we'll kind of look at some volatile examples, make sure we can kind of calculate what happens if we're adding additional pressure into our unknown substance.